Okay, it's 11, so I guess I can start. Um, my topic is memory management through the ages, which really means through the architectures. I am Drew Mason, and after 40 years or so, this is the very first technical talk I've given in a digital equipment context, which is a little amazing. Um, who am I? I started at Digital about 1977 as a summer job working for the group that handled the digital bills of material. And then the following year, I started with commercial engineering, and I had a little bit to do with the initial stages of TDMS and ACMS. And then I became the exec project leader for Ristus E. Leaving that, I was the architect for what we called VAX Secure Virtual System, which is the first instance that I'm aware of putting together a virtual machine host in using today's language for VAX and for VMS. And we spent 6 years doing it or more, and like many good projects, got canceled in field test. I moved from there to the VMS group, where I spent, I think, about 10 years working on, I was the release project leader for Alpha VMS version 1. And I got involved with I/O and memory management and a lot of other interesting things. And then I took a break because it looked to me like with the sale to Compaq, um, um, things weren't going to go well with digital, and I was right. And then after doing a lot of interesting stuff that had nothing to do with VMS for a number of years, I got the call to come down and work with VSI, and I've been there for 10 years and happy as a clam. Yeah, which button does it? Okay. Um, man, there should be a simple one of these buttons that
The arrow keys.
the arrow keys. Okay. Um, so VMS has had almost 50 years of development, and it's fit on 4 architectures: VAX, Alpha, Itanium, and x86. Across that whole period of time, the user's view of memory management has stayed remarkably stable, which is a testament to the smarts of the original developers and the smarts of the people who have maintained it. And it's one of the reasons why people can run their applications after all this time. I'm going to talk about paging, which in the different architectures is rather different. And I'm going to talk about memory protection, which is also different. And I'm going to, in the process, I'm going to touch some assorted topics that are related. So this is a very brief timeline with a focus on memory management. VAX VMS version 1 was announced and shipped in 1977. VAX clusters itself came with VMS version 4 in 84. I know most of you understand how important VAX clusters is, currently called VMS clusters. I believe Oracle's Lock Manager is based on what we did, what we continue to do, and I kind of chuckle when other vendors talk about their clusters offering because very few have anything that's similar. A brief story. Many of you may know this, but when the tragedy of 9/11 came, there were some clusters in the towers that were clustered across the river. Those clusters continued running. That's just awesome. We've had global sections since the beginning. In 1990, we introduced partial sections, which is a section that stops somewhere in the middle of a page. In 92, we brought out our first alpha release. In 93, we brought out page coloring, which I'll talk about a little bit, which is an interesting idea. In 94, we introduced 64-bit addressing. Even though the alpha was a 64-bit machine from the get-go, we started to actually take advantage of it within VMS. In 95, we started seriously moving things into S2 space, the page tables and the global page table for one. In 96, the 64-bit project and system services were starting to roll out 64-bit stuff to the customers. In 97 were buffer objects, which was a key part of fast I/O. In 1999, we introduced RAD-based page allocation, which I'll have a bit more to say later. In 2003, Galaxy came on, which allowed multiple instances of VMS on the same hardware platform. Now, these were not virtual machines in any sense. They were running on the bare hardware, but they were compartmentalized. In 2003, we also brought out version 8 for the Itanium. And then time just kind of drifted on, and digital, compact, HPE. Benign neglect is a polite term for what happened. At any rate, we picked it up in 2014. And in 2021, we brought out the OpenVMS version 9 for the x86. Now, most of you, this is probably incredibly simplistic. But paging is a crucial technology for time sharing. It allows efficient use of both virtual memory and physical memory. You divide both into fixed size chunks, and then different processes can move their memory in and out without running into severe fragmentation issues. On the virtual address, it's called a page. And on the physical address, it's called a page frame, because that's what the virtual memory gets into. So a virtual address is mediated by a page table, which will take the virtual address and figure out where it goes. You take an address, it's divided into a virtual page number and a byte offset. The virtual page number is used to look up in the page table the corresponding physical page frame. And then you combine back the byte offset, and it generates a physical address. And then the hardware does its stuff, and you get the result. VAX, originally called the VAX 11, was an outgrowth of the PDP-11, particularly the 40 and the 70. They didn't really have paging, certainly from the Ristus side. People who might recall overlays, and Rob is nodding his head. I don't know what the corresponding term would have been on RSX.
Overlays.
It was overlays. Okay, well,
same task builder.
Yeah, okay. It's the same idea, pretty much the customer, the application had to manage all of that and decide when to bring in the next overlay. And it was, the PDP-11 was a 16-bit machine, and by the time the VAX came along, it was out of it. It just didn't have any place to go. So the VAX had 32 bits, which was a big change. Page size was 512 bytes. I thought at the time that was small, but it's what they did. 32-bit addresses, which is a virtual address space of 4 gigabytes. It was divided into 3 regions based on the high 2 bits, P0, P1, and S0. And the high 2 bits of a 1, 1 were unused. So it's really 3 gigabytes of effective address. So with 9 bits of byte offset, that left 21 bits of virtual page number or page frame number. And each of those 3 regions was 1 gigabyte. The way paging worked on the VAX was each region had 2 registers, a base and a length. So the system registers contain physical address. So system address started here, it extended here, and if the virtual address was too big, you said, no, you can't have that. Process registers were different. They contained virtual addresses within system space. So system space, it's still true today. S0 space starts at the low end and grows towards the highest address. And that's because of the base and length registers way back in VAX. Process P0 is the same thing. It starts at address 0 and goes to high ones. P1 is backwards. It starts at the high end and then grows towards 0. The low bit in the page table entry indicates whether the PTE itself is valid. And if the low bit is a 0, then that generates a page fault. Software decides whether it's time to bring in a page and where it is. The bits in an invalid PTE tell you some information like, is it in memory on the free list or the modified list? Is it on the backing store? Is it in the page file? Is it the swap file? Is it a demand 0 page? And you put that together with the PFN database and the software knows what to do. All of these concepts were pretty much there from the beginning. There was the working set list, which has more sysgen parameters than you can shake a stick at. It's a per process thing. And the idea is, let's remember, while from the point of view of a PDP 11, VAX had lots of memory. But from our point of view today, it was itsy bitsy bitsy. There was a minimum, a default, a quota, an extent, and that's still true today. The idea is with multiple processes trying to access memory, we don't want to allow any process to take over the virtual memory. So you get so much, and that's the quota. The default is what you start with when you just start up a process. And you get a quota, which is, okay, well, you keep adding pages and we'll let you go up to so much. And then you can't easily get more than that because we want to let other people have space. But then we have yet another one, which is an extent, which says if there is space available in the memory, we'll let you grow a bit more. But if somebody else needs it, then we're going to trim you back. But we won't let you have more working set than extent. And then there's the free list and the modified list. So while we're keeping track of the process's memory, if we decide to remove a page from your virtual memory, it doesn't necessarily get written out. It just stays in memory till we need it. So if you manage to fault it again before it's left, it's either on the free list, which means it's still in memory but is unmodified, or it's on the modified list, which means it's been touched since it was last written out. So we need to keep track of that. And before we can get rid of it entirely, we need to write it out to backing store. All of this there was there from the get-go. On the VAX, we had 4 modes or rings, and I call them rings because they are concentric. If you have kernel mode access, then you have exec, super, and user, and so on. Each PTE had a 4-bit protection code in it, has 16 values, of which one is, well, we don't use that one. Um, um, so because they're concentric, we could fit in all of the codes into 15 values and 4 bits. So I have their kernel write, supervisor read, or executive read, or a special one which means no access. So if you tried to reference through it, it would tell you, no, you're going to get an access violation. A write access means read. So where it says kernel write, that means kernel read as well. And the check is made when the PTE is tried to be referenced through. We had a page file and a swap file. We had global and private sections, and we had lots of system services that allowed the customer, the application, the programmer to take advantage of the memory management services. By the way, I'm open to questions at any time if you have any. So then came Alpha. Um, Alpha was done by digital for digital. And it was a very innovative architecture at the time. It was a RISC machine rather than a CISC machine. VAX had a grand total of 16 registers, of which several already had dedicated uses. The Alpha had a bunch more, which was a big help. Um, um, and it had PAL code, which kind of allowed various privileged things to be emulated. Um, it was very nice in its way. I still have a little business card from I think somebody, maybe Rich Whittick, was handing it out. It's just an Alpha chip, which was the very first 64-bit computer on a chip. Alpha was VAX on steroids. 64-bit addresses, of which 43 bits were effective, which is an 8 terabyte virtual address space. Now we're starting to get into real memory. I remember Dick Hustvedt saying, if you're having performance problems, buy more memory. There are on the Alpha 4 different page sizes. 8, 16, 32, and 64K. VMS chose 8K, which is a 13-bit byte offset. We have some little remnants here and there that talk about the bigger page sizes, but to the best of my knowledge, we don't make use of them, except for one other thing that I will get to. There are 3 levels of page tables and no length registers. And I'll have some pictures in a little bit. We have the gap, which I also have a picture. We have granularity hints, which we use, and a topic that is probably an hour-long talk all by itself, which is the self-mapped level 1 page table. I asked Mike Harvey years ago where he came up with the idea, and he couldn't remember. So I'm dying to know, because it is such an important idea and it's so complicated to explain. But it allows page table space, which I will also talk about. So the virtual address has 43 bits from 0 to 42, and bit 42 must be sign extended. So there is this region 0 to 3FF, whatever it is, that's roughly the process space, and then FFFFFC, blah, blah, to the highest, which is roughly system space. Addresses between there are inaccessible because bit 42 must be sign extended. If you try to generate an address with something either than zeros or ones in that high part, the CPU will just say no in some moderately unfriendly way. And we call that the gap. I asked John, do we had a term for this, and he didn't recall anyone, so I just decided I'll call this virtual address promotion. At this time, VMS was still essentially a 32-bit system. But the hardware is a 64-bit system. So how do we deal with that? Well, when we load an address, we use a load long, which automatically sign extends a 32-bit address to a 64-bit address. So so this here sign extends that top 0-bit to this 64-bit address. That would be a process space address. This sign extends the high bit. Here is a system space address. That was crucial to the VMS development because we didn't have the resources to write a 64-bit operating system de novo. I wish we did. I wish we still do. But it permeates a lot of things that we still have. The alpha had 3 levels of page tables with no length registers. The alpha had resource allocation domains, which I will talk about, and it had the gap. So this is almost true, but the virtual address space P0 is all the way here and starting at address 0. P1 is here with an address of 00000000 F. I think. Every time I have to write it down and look it up. Then we have this whole space here, which is P2 space, which is now available for applications and customers. Then we have these sizes, by the way, are just suggestive, not representative. And then here's the gap. And then here is S2 space, which again is a huge amount of virtual memory that is now available to the operating system. And then S0 and S1 at the very tippy top. People tell me you always draw your things upside down. I said, yeah, I do. I don't know why. So the way this works, there is a processor register called PTBR, which contains the physical address of the level 1 page table. The byte offset is 13 bits. Each of these segments is 10 bits. And then here's the stuff that has to be 0 or 1. So this part of the virtual address is used as an index into this page table. That will generate the physical address of the level 2 page table. And then this generates an index into here, which generates the physical address of the page in the level 3 page table. And then this indexes into here to finally come into a page, a physical address. So by having 3 levels rather than 2, that greatly extends the available virtual memory. By having an 8K page rather than a 512K page, it also greatly extends the available virtual memory. Now, I mentioned granularity hints. It's a block of aligned virtually and physically contiguous memory in 3 possible sizes. And it makes efficient use of the translation buffer because it's essentially a block of PTEs that all resolve to the same part of physical memory. So if you touch any part of that large granularity hint page, that one TB entry can cover the entire space. And we use it for large resident data structures. So for example, the PFN database can do that. And then there are things in the exec called GH regions. And there are a number of sysgen parameters that say GH, this, that, and the other thing. And that sizes those things. And then when we're building the system's memory on boot, we can allocate larger spaces for the GH regions. And that helps with in use of physical memory and virtual memory inside the exec. I am not aware of any use of these outside of the system, but I can't promise that there aren't any. But now, page table space. In the VAX, each process had a page table register and a base and a length that could be anywhere within system space. Page table space collects together all of the page tables into one contiguous, virtually contiguous region. And so the same virtual address in a given process will always go to the same, the PTE for that will always go to the same place. And it means that for a given VA to figure out what PTE maps it, it's simply a matter of masking, shifting, adding, and vice versa. If I have the address of a PTE, by masking, shifting, and adding, I can go directly to what virtual address is it for. Back in the VAX scheme, it wasn't anywhere near so simple. Now, what happened with the alpha was we used page table space to divide system space from process space. So this is a corrected version of the alpha virtual address space. P0, P1, P2, the gap are the same, but there's this area here that is also part of P2 space. Then comes page table space, which is wherever the system designers put it. Yes, John, it really is. And then S2 space and S0 and S1. I don't know to what extent this fraction gets used, but we go to a lot of difficult calculations to make sure that this is available.
I've never seen P2 beyond the gap ever used.
Neither have I, but I know the calculations. Now, VMS was, and to a large extent still is, a 32-bit operating system. We have page table here that is clearly in 64-bit space. In order to touch it, you have to generate a 64-bit address. But lots of things like IO request packets and lots of data structures want to look at PTEs using a 32-bit address. So what did we do? We created something called the SPT window. And it's addressing the problem of how to reference system page table entries with a 32-bit address. It's needed by drivers. And what we do is double map those PTEs into S0 space, or actually S1 space. And then we come up with the SVAPD, the system virtual address of a PTE. So this orange part are the level 3 PTEs for just S0 and S1 space. By the magic of double mapping, we also map the very same PTEs here. So either this address which is a 64-bit virtual address, can touch these PTEs, or a 32-bit address can touch the very same PTEs using a 32-bit address. This allowed us to not have to rewrite the entire I/O system when we started taking advantage of 64 bits. Memory protection on Alpha. This was 4 bidigital, 4 digital. We still had 4 modes. We had 8 bits of protection code. Read and write enable for each mode was independently enabled. So we could effectively generate the same 15 codes as VAX, but you could also generate write-only memory, at least in the PTE. I have never seen it used. I have never heard of it being used, but it's clearly there in the hardware. We also had fault on write, fault on read, fault on execute bits that we could use for various purposes. We could use fault on write, depending on some other context, for fault on write pages. In other words, until you actually modify it, it's fine and everybody can touch it fine. But once you touch it, then you get your own private copy. Fault on execute was a way to enforce no execute access. We introduced 64-bit system services. So we enhanced selected services for 64-bit addresses. So the change mode services, all of the memory management services started taking 64 bits, so you could actually use P2 space. We introduced at buffer objects, which were part of fast I/O. We introduced regions, or this is different from S0, S1 region. These are regions that you can allocate at boot time for specific purposes. Now, page coloring. This was an idea out of the computer science research community. And the problem at the time was direct mapped caches. Direct map cache meant given an address, it went to exactly one cache entry. And if your application used a bunch of addresses that all mapped to the same cache entry, then running it, you were busy thrashing in the cache. So that was a bad idea. And what you did instead was you colored your page according to which cache entry it went to. And then you tried to arrange your application so that it went to different cache entries rather than the same one. And that was an interesting idea, but that got superseded when the industry caches started going to associative memory caches and so on. At that point, this idea was no longer relevant, so we turned it off. But it'll come back. Also, a new idea at the time was non-uniform memory access, or NUMA. And you see that in the alpha, and you see that in spades on the Itanium. The idea is, depending on which address you're referencing, it may take a longer time to reference something. On Itanium, I could see it because we'd have a card that would have a few CPUs and some memory on it. Access within the card was fine, it was as fast as it could get. But if you tried to access reference memory on a different card, it took longer. And so this CPU might have a 1x value memory access time to memory A, but it might be 5x. And I've seen numbers that high. I've seen numbers higher than that to talk to memory B. And what you want to do then is set up your system so that your application running on this CPU is referencing this memory, and not that memory. These were called resource allocation domains, or RADs. So for each access group, where access group or domain may contain a CPU or a memory or both, we create a separate domain, and then we allow CPU affinity to the domain. And then for best performance, you allocate the memory closest to the CPU. And then we took a step further, which is non-page pool is accessed all over the place. So for the read-only parts of non-page pool, we duplicated it so that each domain had its own copy. So non-page pool was as close as we could make it for your process. That's a quick summary of alpha. Now we come to Itanium, which was a system not by digital and not for digital. Now, I will say right here, integrity is a marketing term and it is a null value. I thought it used to have some value, but as soon as HP came out with the Integrity ProLiant series, it's like, no, the ProLiant is an x86. So it's not an Itanium, it's not so an Integrity x86. Anyway, this is another very interesting architecture academically, and I wish it had been a commercial success. It has a bunch of new ideas that went beyond the alpha. The register stack is very interesting. It had more registers than you could shake a stick at. Which is good for fast calls. It's good for argument passing. It's not so good for process context switches. Um, but they had enough, the architecture of the system itself is very different. The issuing of 3 instructions at once, that required a step up in terms of the complexity and intelligence of the compilers. On the Itanium, it also had 64-bit addresses, and at the hardware level, it had a huge range of page sizes to choose from. It also had no page tables in hardware. VMS chose an 8K page size because we had this huge investment in 8K pages. So how was that, with no page tables, VMS is a page table system. What do we do? Well, there's the translation look aside buffer. And there's also a virtual hash page table. These are in memory. So the TLB is just an address cache. The virtual page table hash is essentially another cache for addresses that is managed by software but accessed by hardware. So what we did was we generated the page tables in software using the same page table space and so on. And what the hardware does is it takes a hash of the virtual address to search the instruction TLB or the data TLB. If it fails, then it takes another hash of the virtual address to search the virtual hash page table. And if it can't find what it's looking for there, it faults to software. And then the software runs through the 3 levels of page table to generate, oh, okay, this virtual address corresponds to that physical address and all kinds of protection bits and so on. It loads the virtual hash page table and restarts. So it's like, okay, talk about different. So that was another major piece of work that had to be done. It's like, how do we keep VMS on a system that is just so different? So with the same 3-level page tables, there we have the same gap. There are no granularity hints on this system. So we already had the granularity hint regions for the system. We just kept them. And it didn't hurt. but we had, we kept the page table space with the self-mapped page tables. And Itanium made much more use of RADs than Alpha did, I believe. Am I doing on time? I have no idea.
20 minutes left.
20 minutes left. 2 architectures to go. So again, there is, hello, did I run out of battery already? Fresh batteries. Okay. The same SPT window for double mapping. In this case, process space is entirely at lower addresses in the gap. So everything, there is no space between the gap and page table space, and then S2 space fills up the entire space in between. Itanium has more or less 4 modes, and it does it with 5 bits, 3 bits of access rights and 2 bits of privilege level. Privilege level is equivalent to mode, 0, 1, 2, 3. Access right is a little different. And in there, we only have 8 values. It adds an execute permission and also promote permission, which is essentially how we do change mode. But because of only having those 8 codes, some VAX codes simply aren't available. They don't exist. And for example, supervisor read kernel write is not available on the Itanium. We had to squish it into supervisor read exec write. And same with supervisor read exec write or kernel write. We had to squish them into user read supervisor write. x86 brought its own challenges. Now, I had the advantage of looking back at Itanium and Alpha to see what was done. x86, this was, we had to figure out how to do it in the without much help. There were 2 major challenges. Paging is different yet again, and there are only 2 modes in hardware. We looked carefully at making VMS a 2-mode system, and we decided that that was just a bridge too far. It's just not something we wanted to do. We disabled swapping. The code's still there, but we don't do it. If you have a problem with fitting your application in, page pool isn't page. We looked at it. There really isn't much left in it, so it's permanently not paged. We removed the SPT window, which I will talk about in a little bit, and there are no RADs for now. Now, I know the x86 systems have them, but I haven't seen them on virtual machines. They may exist, but I haven't seen them in the guest. So, and enabling them is a lot of work that we would have to do. So for now, we don't worry about that. Paging on x86 is a 64-bit address, has a bigger effective address. So we have a 256 terabyte virtual address. The hardware page sizes are 4K, 2 megs, and 1 gig. You can have 4 or 5 levels of page table. We thought about that at the time when we were starting. They talked about 5 levels, but they didn't actually provide us a way to do it. I'm not quite sure they do yet, but it's certainly in the architecture. So what do we do about a 4K page size? And we talked about it and thought about it and said, the 8K page size is just too ingrained in VMS to get rid of. Too many things depend on it, too many system services, too many parts of the exec. So, okay, what can we do? So we treat two adjacent hardware pages as one 8K page. They have to be an even odd pair. So, page 20 and page 21, they're combined into a single 8K page. The PTEs have to have exactly the same bits, except the PFN of the second one is one higher than the other. So rather than having to rototill the entire system, we just had to rework most of memory management internals. 4 levels of page table with a 4K page. Of course, they renamed everything too, so we don't have levels 1, 2, 3, and 4. We have the bottom page table. We have the page directory. We have the page directory page table and the page mapping level 4. And if they have 5, then it's the page mapping level 5. And once again, we sign extend bit 47 in this case. So that whole field has to be a 0 or a 1. Just like the alpha, the PTBR register, it has a different name, has the physical address of the PML4. The PML4 page, which is indexed by PML4E entry, that will give you the address of the PDPTE, and then that indexed will give you the address of the page directory entry, and that index will give you the page of the bottom page table, which will finally give you the page address, the physical address. But wait, there's more. The architecture allows you to have a 2 meg page. There is a bit in the page directory entry that says, oh, I'm not the address of a bottom page table entry. I'm the address of physical memory. So we just bypass the bottom page table entry, and you now have a 2 meg page. So it has to be virtually and physically contiguous. We are, yes. But wait, there's more. You can have a gigabyte page. We are not using that at this time, but it's the same idea. There's a bit in the PDPTE that says, I'm going to physical memory. I'm not going to a page directory entry. So you have a gigabyte page. So as far as VMS is concerned, we have 3 page sizes, 8K, 4 megs, and 2 gigs. The users see no changes because it's just 8K pages. Upper levels of the operating system see little change. There's some things where they have to have some knowledge, but the inner parts of memory management were rototilled. What do we use them for? The selected granularity hit regions, that comes back, so we can take advantage of that. The coming with 923, the PFN database is in 4 meg pages. Buffer objects, I think, are a prime candidate for this. In fact, if you have a big enough buffer object, you could have a 1 gig page. There are no plans on the drawing board, just kind of ideas in my head. Other memory resident data structures are candidates, and if buffer objects can do it, then FastIO can do it. Now we come back to the SVAPT problem. IO relied on the SPT window in order to allow 32-bit addresses in ERPs to reference page tables. So as a major change to the IO subsystem, we replace the SVAPT with an IO buffer descriptor. And I will defer the discussion of that to Dave Fairbanks' talk, which is later today, who will go into greater detail on that. But it is a new way of accessing IO, and it applies to both direct and buffered IO. And as Dave and Rick, the late Rick Lord, and I put this together, we think it's great. Memory protection. VMS requires 4 modes and x86 only has 2. And of course, they call them supervisor and user, and that confuses everybody. And what makes it worse is the PTE only has 2 bits, a read and write bit and a user or supervisor bit. There is no way in the PTE to say no access, unless you simply make it invalid. There is an execute bit in the page table entry, and that's like, now what? Well, we could have tried to make VMS a 2-mode system. We looked at that and decided pretty quickly, no, we're not going to do that. So instead, we compress the access mode. VMS kernel goes into the x86 supervisor, and then VMS exec super user go into the x86 user mode. Why did we divide it that way? Well, x86 supervisor mode has access to privileged instructions. So we wanted to make sure that RMS and DCL did not have access to privileged instructions. We have 4 complete sets of page tables with appropriate access. So every time you change mode exec, whatever, we reload your page tables. Is this a performance drag? You betcha. We do take advantage of the PCID, which is the x86 term for address space match. Each job gets an identifier, and if it gets swapped out and then brought back in, its identifier, if the cache entries are still there, they're still there, and it says, oh, okay, I recognize you. And then there's a global bit as well that says for every process, this will map in the TLB. So as a summary, after 50 years of development across 4 very different architectures, we're almost the same. Now, you can still use your 32-bit services in a 32-bit way in your applications. And we've provided you some new features just within memory management. Questions?
Okay, I have a question.
Yes, sir.
My name's Ian Smith from Oracle.
Yeah.
So the Oracle IDB product runs in user mode and does change mode to exec.
Yeah.
For
a lot.
Thousands and thousands of calls.
Yes.
So how much of a hit is this on x86?
Well, now you're talking about performance measurement, and I'm looking at the guy who is probably our lead performance measurer. It's a hit, there's no doubt. And one of our active projects is try and figure out how to make change mode faster.
Because on Titanium, like you said, like the promote page, and you have this EPC instruction, execute privilege. So we didn't really go through the expensive Swiss, what we have now built in software, to do basically change mode. It doesn't matter if we change mode to exec or change mode to kernel, it's the same hit. So yes, there is a hit, and
we're aware of the problem, and our best minds are actively working it, but I don't have an answer for you right now.
Used. So, thank you.
What was news? There
was a hit.
Oh yeah.
hits in other places too.
Yeah. Right. But if your application does a lot in terms of change mode, yeah, you're gonna see it.
Just stay there.
Well, we can't. That's the
I know.
We have to start.
I know.
Our applications.
Yes, sir.
Is there instrumentation available to just do like a trace of typical runtime to see how well the cache that you were talking about would work.
Well, let me hedge that. The For a variety of reasons, the clock on the virtual machine runs slow. It ticks slow, let me put that way. The clock on a bare hardware runs at a millisecond a tick, and virtual machine, it runs at 10 milliseconds a tick. So at a 10 millisecond tick, that's a pretty, on a machine that fast, you're getting a pretty blurry view. Now, we are working on a way to let you tweak that for the sysgen parameter. I don't know that it's available in 9.2.3.
It's not.
Is,
Okay,
no, it is not, yeah.
It will be in the first updates.
okay,
But what, yeah, that's also.
The hardware still has to perform.
Hardware also, right now, it's chip count.
Then you can cache, this is cache.
Like the chip counter only have, active on virtual guests which run at least an X2 APIC. Like a virtual box doesn't have the chip.
Virtualization makes it harder for us to measure accurate performance characteristics because of that distance.
yeah,
I think it's easier to measure on a bare system, but on a virtual system, the extra layer, again, adds another layer of fuzziness to the whole.
But even like with the tick, because like the hardware still runs in cycles, so you can still use the chip count to measure at a much finer granularity. But this is also, that stuff is also not in 9.2.3, but we can make it available in update or whatever the.
what tools do we have? Do we have?
Right now in 9.2.3,
Yeah,
chips,
yeah.
we have this PCS,
Yeah,
PC sampling, which is on a tick, the lowest, the finest granularity is 1 tick,
yeah,
which is 10 millisecond on a virtual machine,
right,
which is a lifetime in
Yeah.
days.
it is. Anyway,
Next, there's not for lunch.
lunch, yeah, lunch.
Yeah, it's 12 inch lunches.
Anyway, I'll be happy to stay and chat with anybody who has more to talk about on the topic. Look on the calendar right on the door.
Deadlines.